Pleasure of mine to introduce my friend Anna Dyson. She is absolutely a dynamo of a person that I have the great privilege every once in a while to hang out with and talk about all the amazing things that you'll hear about today that she does in her research spanning architecture, engineering, ecology, systems thinking. She is the Hines Professor of Architecture at the School of Architecture at Yale, where she founded and directs the Center for Ecosystems in Architecture. I originally met her when she was running this fantastic Institute for Research in New York City at the SOM office as part of her role as a professor at RPI. And a lot of that is translated into many ongoing projects with amazing people around the world. And she has received numerous awards. I think one of the most impressive things as a researcher here and I guess I didn't introduce myself, I'm Forrest Meggers. I'm jointly appointed faculty between architecture and the Andlinger Center here at Princeton. And in that role, I appreciate very much the hard work it takes to get Department of Energy awards and NSF awards, while at the same time winning American Institute of Architecture recognitions and prizes. So Anna's really spanned the gamut in terms of amazing output in the context of buildings and our environment. And I'm really proud to be able to have her here today and to introduce her. So thank you so much, Anna, for joining us. I very much look forward to seeing again all the fantastic work you're producing. Thanks.
Thank you so much, Forrest. That was an incredible introduction. Hope I can live up to that. So I'm going to share my screen now and do something that I've never done before. I can't even find it. Here we are, Firefox. And I'm going to start with our website. And the reason why I'm not going to dive right into a PowerPoint the way that we normally do and share our work is because I think that the challenge that we have towards ecosystems thinking really gets sort of reinforced at every step of the way in terms of the way we communicate, the way we look at things, and the way we present our work. And I realized when a colleague of mine, Jason Bolin, who is the head of the innovation lab at AECOM, presented at Yale last week, he presented literally kind of laterally from a kind of web format. And immediately you could see more of the context of the work. So I'm going to start with the first half. I'm going to just do really introductory overview of the context within which we're working. And then I'm going to dive deep into well, as deeply as you can in 20 minutes into a quick case study. But we'll be more looking at kind of, how we go deep. So the big challenge for us is that as architects, we have to deliver the entire ecosystem, whether we know how it's performing or what it does or not. We're holding the ball. We're the ones specifying, we're the recipient specifiers of products. And that really is, in a sense, the motivating factor towards the research, how I got into research several decades ago, is because we ultimately realized that we were specifying products that had been, and we would sort of distribute them within urban systems and within buildings. They were systems and devices and materials that had been conceived of kind of individually, kind of in their own, in a sense, conceptual framework, as opposed to ecosystemically or how they would be interacting with other things. And so even just the way that we look at things, we're sort of developing new formats here as a studio in what we're calling BEAM Lab, or Built Environment Ecosystems Measurements Lab. Show that in a minute. And the way that we work, we've started in a sense by creating formats that are immersive, within which we literally can inhabit and understand the information with multiple people looking at the information through obviously the baggage and the lens that they're bringing to the table through their disciplinary backgrounds and their cultural backgrounds. And then sort of our first pass is, can we be under one roof, quote unquote? That was a term that was introduced by the Department of Energy with their big hubs that their hub competitions, probably 15 years ago now. But that idea that we could have many different folks working in many different aspects. This is just a snapshot of our space, a studio where you can see that there are PhD students, postdocs, research scientists, and also some design students that are working on different systems. They're working on plant-based air and water remediation systems. They're working on solar energy systems, but they're kind of in the same space. And so it sounds really basic, but can we occupy, labs that are literally transdisciplinary or spaces that are transdisciplinary? Of course, there's a lot of people that we work with, and the majority of the people that we work with actually are not architects by training. This is just on our website, sort of the core people that we really work with day in and day out. There's a lot of other people associated with our center that are sort of the networks that each person brings to the table. But then even in terms of the products that we, how do we actually share our discoveries and our research? You can see that immediately we cannot have one format. We have to have literally formats that are expecting completely different information and formats for what is essentially the same work. Right here, you can see there's a long list of architectural publications. And once again, you'll see that it's very, very product oriented. I'm going to focus at the end of my lecture on this case study where we're looking at plants. It's centuries of research really going into how would we restitch our relationship with non-human living systems through buildings and cities after having spent literally millennia trying to keep living systems processes out of our systems. And maybe the sort of end game of that has been the mechanical and electrical paradigm that we're stuck with now, incredibly energy intensive and not really working too well in terms of its relationship to biodiversity or on-site net zero or any of these major societal goals that we have. But like these formats, looking at it through the lens of a bunch of different criteria and factors, let's see what happens when we have to present the exact same work, let's say in the context of a scientific forum, where at the end of the day, there's going to be a tremendous pressure to frame things in a very, very different way. Here, of course, what we're framing is kind of results that we get. In this case, I'm using this as a first case study just to, sorry, I'll click on this graphical abstract. Trying to click on it. I guess it's, this is a first case study as an example, just of how we are so desperately as architects trying to develop systems that would have ecosystemic criteria by ganging together a lot of different individually sort of developed systems. So as opposed to, let's say, a solar panel that you put on your roof that will deliver, let's say, between 14 to 25% efficiency. This is definitely not a system that was developed with buildings in mind, because if you think of buildings, what do we really need on buildings? We need much more than electricity. We actually do need the heat that is being wasted off of our typical photovoltaics or other things. So this is a system that's looking at that building envelope, not putting a single function or sort of some simple system on, but how do you really look at that building envelope as an ecosystemic condition within which you need daylighting to get started, a connection to views, a connection to the outside. You need cool diffuse daylighting, so you need to be able to often modulate that heat. Sometimes you want the heat, sometimes you don't. Sometimes the light is not coming in the right direction or with the characteristics that you need. It has too much glare or it is too intense. And of course, you need very high, what we would call high quality energy coming from our conventional systems, electricity and maybe high temperature heat to drive systems for all the things you need to do inside a building, heating, cooling, lighting, plug loads, etc. So how can we basically look at it as we are shaping energy flows, that we think about our buildings as literally transfer functions or as building envelopes that are interdependent with the outside, and that we're going to kind of mediate what's coming inside, i.e. on the left-hand side, the solar resource with all of the different things that we need to do on the inside. So, when we look at that, what can we do with existing technologies? This is literally an applications type of research, right? We're taking optics, semiconductor, other things that are doing pretty well on their own, trying to gang them all up together. We hadn't been previously in fundamental materials research, although we've moved over to that as well, trying to embed these ecosystemic criteria in the development of the materials themselves. But ultimately, we've still got something like, over 71% efficiency combined heat and power if we look at, what we are able to do with existing systems. But once again, at the end game of that, we're doing we're only taking care of a small slice of what we actually need to do inside the interior. So just to go back a little bit to the context and to say, what is the driving sort of motivation behind this research? We tend to sort of categorize our research in these different categories. But as I said, as architects, we need to have all of these categories, and we need to integrate them all into systems. We need to decide what will the materials be. We have to be able to deliver safe energy, reliable, safe air and water quality, et cetera. And increasingly, we are learning more and more about how that interrelationship between our environment and our biology is interdependent. So looking at also going in a deeper dive between the relationship with what I just just showed, what can we do with existing, if we were thinking ecosystemically with what we can do with existing technologies and not think about them individually, we immediately get sort of put into a bind of the limitations of our existing material systems as individual things. So taking the exact same criteria, how do we render that building on-site net zero, if you will, or work with the type of energy that we have ambiently? That starts to send us into really looking at a kind of bioresponsive framework, tightly coupling in time lighting demands and cooling demands and other interior conditions. But what do we have to do literally in order to have enough handles on the energies simultaneously? We have to go literally all the way down to subatomic scale. And we have to think about how are we going to manipulate those energy flows? Because if we want to get to on-site net zero, all we really have is what is at that building envelope, and how are we going to couple that or match it, if you will, with the interior conditions. So this is another, maybe just a visualization of how a micro scale system would work. Here, we're still in the micro scale. We're not in that very, very small scale where we can do many things, but we can do a lot more than what we just showed with the IC solar facade system, that is literally kind of just assembling, if you will, the optics, the semiconductor, et cetera. And here what we can see is that if we want to manipulate the energy flows, there will be a relationship for sure between what we see and what we can do as a kind of cultural artifact, as we showed at the beginning, what the world will care about, and what the architects will ultimately specify will be a cultural product. It will be something that is socially valuable, either as a kind of technical condition or as an aesthetic or cultural condition. But if you think about once again, what we do on a building envelope, we do not at all need the same things throughout, let's even say a diurnal swing. We need very, very different things. So developing materials that can, once again, absorb or capture, transform, and store and redistribute these energy flows according to a lot of different criteria is really where we're at, in a sense, with the research now. And once again, going back to the scientific formats, we will publish maybe one aspect of it. This is just one format that is where we're looking literally at trying to disassociate, in this case, the visible transmission from the solar heat gain coefficient, or other types of things. Put in very simple terms, you might want to either absorb heat or reject heat, but you might want to keep your window clear, or you might want to have it opaque. Those types of things might want to be disassociated, as just a very simple example of what we would want to do on a building envelope, in order, in a sense, ultimately, to provide a condition that is both technically i.e. dramatically lowering energy consumption, carbon footprint, transforming the available clean renewable energy, and what the cultural requirements will be, let's say for privacy or for transparency or for a comfortable daylight. So you can see that there's so many different criteria, right, that we have here in that building envelope. If we were literally going to really, in a sense, stretch that energy. So what I guess I'm trying to say is that a lot of times we might think about it in a purely technical framework and think about stretching that energy from purely technical standpoint. But when we start to look at that intersection and literally embed many of these social criteria into the lab and into the development of the materials, we can now start to see that we can gain so much value that was unanticipated, right? That these kinds of materials and these systems do things that might not have seemed valuable within the context, within another sort of framework for the criteria for development, but it becomes very, very valuable when we start to think about it in other terms. So just going into ultimately also, so we've got the research, and the research is coming from so many different fields, as we've said. If we had to think across biotic and abiotic systems, if we had to think about multiple scales, ultimately we've got a very, very complex network or interrelationship of flows, of information flows. But what is really tricky for us as architects is we know with all of these systems that we cannot just test at one scale. We have to be testing at multiple scales. And typically the kinds of tests that we are effectuating are going to be going all the way down from literally the smallest of clean room scales, let's say at that nano, typically into some sort of micro scale of a small chamber, then what we would call a larger controlled chamber, which is a room. I can, show this, let's just show that right here. In Public Safety Answering Center as an example. And then in this case, with the Public Safety Answering Center, we're going into what is probably the largest terrestrial environment that we have to be quite controlled. And the reason why we're controlled in the Public Safety Answering Center here, this is in the Bronx, it's a building in the Bronx, you're looking at the interior, is that it has a programmatic requirement to have to shut off the fresh air intake in case of any type of compromised event on the outside. We can think of 9/11, we can think of Fukushima, we can think of all sorts of things that would be compromising and that you need to, this is basically the control command center for Greater New York. It's the redundant one. The last one was in the towers, which is one of the reasons it was so chaotic following the attacks. But this would be an example of where we could potentially shut down. We have the ability to shut down this whole zone. So it's a zone within a building. And this is literally a scientific experiment. It doesn't look like it, right? But what we're doing is we're trying to interrelate and test the relationship between all of the different constituents of the air quality and how these organisms, in the case of, it's mostly the rhizosphere, the microbial conditions within the rhizosphere are reforming some of the sort of problematic aspects of the air quality. A good example would be VOCs, for example. So we'll just show that as an example of how we parallel track like a building like that, which is pretty much an open system. Our buildings are very open. We try to pretend that they're closed when we're counting the HVAC and other things, but typically what we've been doing, all of our sort of within the mechanical paradigm is we try to minimize entropy production. We're trying to minimize losses, right? So we're throwing a lot of energy at an HVAC system, and then we try to create maybe tightness or insulation around different sort of envelopes, et cetera. But in this case, we're inverting the condition where we're literally using that idea of a closed loop system, which is really not closed as we said, but we pretend that it is, in order to test, can we actually remediate or produce the fresh air from within the building? So there will be all sorts of constituents of the lab that we'd have to test in a very controlled environment. We might be lucky and have certain room scale environments that are very, very well-controlled, or we can create a somewhat controlled condition at the room scale, but that's going to be less controlled, of course. As we start going out to the building scale, we get less and less control and over the sort of inputs and outputs within the system, and really starting to understand those relationships between variables. But here we are at PSEC 2, as I said, in the zone scale, where we're really at that zone scale. Why is it interesting for us to be there? Well, it ends up that it's interesting to be there because we're able to then literally test with people. And that's, before I get into the case study, I will just run through a few more projects to show how that happens, how we look at that relationship between behaviors and people and how we're doing. I'm just going to use this example of the public school 62. So this is a very interesting project, and it does absolutely highlight the limitations of our existing systems and the motivations, because you can see that this was, although it was the first zero energy school in the or institution of any kind in the Northeast, actually, you can see it requires almost a football field for on-site net zero, right? It's not necessarily a prototype for so-called ubiquitous application or general application. We can also see that each system is developed kind of independently of each other, right? And they're put together, but you could imagine, for example, fortunately, this is quite a windy site, but in a hot, humid environment, if the wind is not blowing, we're going to have a tremendous amount of waste heat around these dark surfaces that might actually drive up our air conditioning, the exact opposite that we're trying to do, right, with an on-site net zero. So you can see all the conflicts that are involved, right, in all of these systems. They cancel each other out. They don't really work well together in the sandbox. But this is an example of where we're at literally with the existing technologies. If we were to then go to, sorry, if we were to go into an environment, excuse me. I said I wouldn't do this during the presentation, but I've made it skip all over the place. Let me just go back to project. So another maybe more productive case study would be something like Botswana Innovation Hub, where we don't have a pre-existing grid. So there's a tremendous opportunity here to really rethink that relationship between the context, the natural context, and all of the different ecosystems conditions within that. And so here we can see in Botswana where we are visualizing a lot of emerging systems that we actually didn't have sort of ready. That solar facade that you just saw in renewable energy was visualized and calculated for these clerestory windows that you see, and we weren't quite ready in time. So this is another really important thing about built environment, is that we need to think about our buildings as being evolutionary and adopting the new technologies as they come. But this is a very interesting case study too, because once again, you can see that we're thinking about it from scratch. We are not dependent on necessarily a lot of entrenched interest in the grid or in what is happening there. So there's an opportunity to rethink on-site net zero more considerably, although it was really the limitations of the technologies themselves that at the time of construction that limited that. Now, finally, probably the most precipitous, I think I'm running out of time, right? How many more? Oh, okay, yeah, so I think I'm gonna move over to my PowerPoint in a minute, but just if you have time to go and look at Aerospace City on our website, if you're interested in that, that then starts to show literally a 20-year project that looks at that interrelationship between material choices, energy systems, building scale, and then district scale, which is ultimately, if we are to solve our so-called on-site net zero or renewable challenge, we have to be going back and forth, literally from the smallest of material all the way up to district and possibly even regional in most climate types and in most projects and most building types. And I would say that that also what is really, really critical that we think about really is what will drive what are the, for us, because we come initially from, in a sense, the deployment sector and architecture, we think about what will drive, in a sense, these transitions, and what are the major, let's say, hiccups to all of that. So I'm just going to go into ecosystem here, just to say that so much of what we do also is working on the virtual frameworks, working on the virtual frameworks. Like, how are we going to basically get, because we would think even new projects like Botswana Technology Hub, or where you have, a real, one might think it's a tabula rasa, but we always think about actually that because there's so many interdependencies between all of the different ways that we do things, that everything that we do is literally not just a physical retrofit, but it's a mental retrofit, meaning that we have ways of working and we have a lot of people developing models in a lot of different ways. But what we're developing literally is, how can we get models and model attributes to talk to each other? How can we move away from this kind of pyramid system? And I think that this pyramid system, I'm just showing the architect there, but I think that this applies to so many different siloed disciplines that we have, whereby you really have this kind of relationship, this kind of hierarchical relationship of information that is kind of traveling up the pyramid, if you will, as opposed to really thinking we've got a cacophony if we try to actually get all of our models and our model attributes talking to each other. So how do we actually develop semantics, and how do we develop interoperability so that we can speak to each other in these sort of large scale frameworks? And just on our last note before I transition, ultimately, in creating these frameworks, we're very well placed actually within architecture, because we do have highly detailed data sets, very, very high resolution data sets going all the way out to urban. And then increasingly with data collection and Internet of Things, we're increasingly getting a tremendous amount of noise, of course, tremendous noise in the collection of data, sort of ubiquitously within buildings. But it's kind of undeniable that the sensors, that there's this incredible race in sensing and controls globally across all of the different fields, and they really are getting better and better. And so we're getting more and more information, and we're getting better and better information. And to be able to create these frameworks, these kind of semantic frameworks, where we can really start to get like analytics and metrics, we can get sort of all the different ways of modeling things. It's hard to see this, I apologize, but maybe we could, on the next, you can see that these are just screen captures from SEVA, or socio-ecological visualization analytics, which is literally the sort of virtual framework in order to get these vastly different sort of disciplines and folks working together. You might have many different ways of modeling similar information. And how can you literally start to understand, and we have these fitness tickets, fitness around data, so that you can really understand the context around both data acquisition and models, and be able to trade them across really unlike disciplines. And so we're creating also that kind of global framework. This happens to be with the Gates Foundation with their Healthy Birth, Growth and Development Initiative, where we can start to literally understand that relationship between what we would call microdata. Data scientists don't like us saying that, but literally the data acquisition, let's say from a biometric or from an environment, all the way out to the sort of aggregated statistics, or very large data sets, or historical data sets as well. It makes, in our view, historical data even more relevant if we start to be able to create these frameworks for contextualizing it in the context of new discoveries, and in the context of more information into the system. So I am then going to stop share and go to the PowerPoint real quick to do a deep dive. And it should be this one, right? This one, yeah. Okay. I'll have to go back up. Sorry, it's good. Okay. Yeah. So how do we, what is an example of how we might create a test bed that would be ecosystemic, and where it would really start to allow people to actually co-develop, not apply materials devices into integrated systems, but actually start to think of the emergence of materials and devices within the context of ecosystems. So very, very different distinction. There are two different types of things that we tend to do. Sorry, we are either trying, as I said, with the sort of icy solar facade, or that first one, trying to get ecosystemic behaviors from mechanical and electrical, sort of in optical paradigms, or in some cases, we're trying to put behaviors, which are biological, which are organismic, that evolved over millennia, or evolved over the sort of the course of history, ecosystemically into our non-ecosystemic frameworks. So not that easy, for example, to put plants even into a mechanical and electrical environment. Why is that the case? Actually, our biologist friends will say plants can be dangerous. As anyone with seasonal allergies or mold allergies or other things could tell you. But it turns out actually that the absence of plants is very dangerous for us too. And we're hearing more and more about this from all over the world. Incredible research, I think some of the most interesting from the Hines group in Finland, looking, for example, looking at the so-called biodiversity hypothesis, or that interrelationship between human health and well-being. And in the case of Hines, they've correlated to the presence of rare flowering plants. That's not just any old green, it's rare flowering plants are being interrelated in longitudinal studies with human immunity and health and well-being. Really incredible stuff. So what we realize actually that is very, very recent, that we've actually only started spending time, massive amounts of time indoors. In our case, it could be well over 90% in this climate type. And they are very, very low biodiverse environments, right? So, sorry. Am I going in the wrong? Sorry. There are low biodiversity environments. In a sense, we could almost think about New York City outside of Central Park as being a kind of Brownsfield site, right? We could say maybe it's a Brownsfield site for humans. We have a lot of biologicals in our buildings, us and our parasites is what we find microbially, right? Here we're exchanging microbiome. I hope I haven't exchanged too much microbiome with you, but we do if we all had our masks off and with all of the sort of shedding that we'd have inside the environment, skin shedding and other things, we are contributing a lot of microbiome to this environment, which we are sharing. But this environment that we're sitting in here is very, very low in biodiversity. And even if we were to open a window, if that were operable over there, we might see something blowing in from the outside, from the soils or from the trees or other things, but it would only really reach a few feet away from that's what we're also finding, that there's not much spread of the outside microbiome, even if we open our windows. So as we said, I'm not going to belabor this point because we talked about this whole issue of interscalar relationships, but you can imagine just how complex this starts to get, right? If we're going all the way into the source emissions or into our biochemical condition of human beings and others inside, all the way out to global, we are literally relying. We could think, you should ask yourself the question always when you're in an environment, where's your oxygen coming from? Where's the biodiversity coming from? Oftentimes it can be from really far away. This is a nice, I think, image that shows our challenge as urbanists and architects. An image like this is literally showing a biodiverse airstream, and look where it is. It's certainly not within the canyons or within the sort of lower levels of urban environments and buildings. So we're shaping also our biodiversity within cities and buildings. And actually just going back to this really interesting data coming, also correlating. There's great data coming out of Switzerland and Zurich that shows not just in high-rise environments like New York City, but in a so-called low-rise environment like Zurich, where all of the buildings are a similar height, they have correlated life expectancy to the floor on which you're living. So that is actually largely also an issue of the problem that you have within these sort of low rise environments is you have a lot of skimming flow. So also you don't have to be living in an environment like New York to be missing that really good ex-urban air quality, stream. So one of the things that a big question we know and that we cannot take care of, even let's say if we wouldn't even think about microbial diversity. Certain things like VOCs and other things are just not well taken care of by our buildings. And ultimately, we're designing buildings for humans, right? Human beings largely. But what we're doing here, if you can see, is we're trying to actually start to say, okay, can we within occupied spaces really start to say, if we had to construct an ecology, if we had to build an ecology that would be biodiverse, what are, just to get started, within our live spaces? Here you can see a conference room, and then you can see a box. We call this the breathe box because we had to take the plant. We started these kinds of experiments with plants in the environment, but we immediately saw that there was a biophilia reaction, or basically some subjects, especially in the middle of winter, would just look at a green wall and we would see a response in breathing rate and heart rate variability. It was really incredible. So we had to actually start to run these studies without the subjects even knowing the plants were part of the study. So they're completely in another chamber. And you can see all the different types of measurements that we're taking, right? The human health measurements, the plant-based measurements, and then the built environment measurements. And then, of course, the microbiome, which is kind of an interrelationship between, in a way, all three things. Because we start to get a lot of mixing from the outside. So there's some mixing from the outside, tiny bit, and for what we're doing. And so ultimately, this is maybe an easier way to say that. We just set that up for PSAC 2, for that big green wall that you saw earlier, because we wanted to this was just a pilot study to try to prepare for potential longitudinal studies that would involve hundreds, if not, well, actually thousands of subjects over the course of quite a long time in the PSAC 2. So we really were not expecting to find anything here. Like, what are we going to find in 3 days, right? The protocol setup was that we would have, a typical fresh air supply of what you have. This happens to be a lab building. It's in the Center for Biotechnology and Interdisciplinary Studies. So it's kind of what we would say the Maserati of HVACs, right? It's 100% exterior air, upstate New York, beautiful, beautiful stream that you're getting in there for day one. Day two, we have recirculated air, which would actually resemble a lot of the environment, many more of the environments than we think that we actually live in our houses and in certain types of commercial environments that don't have adequate exterior air. And then the third day, where we're pumping air into that chamber from the breathe box, from the plant wall. And this is an example of how it was set up. A little bit of a jerry rig because it's a pilot. Here we are inside. You can see what we're doing here, actually, which is probably worth noting, but this is long-term research that is showing that because of the surface area of root rhizospheres and the amount of activity that you have in the root rhizosphere and in the root zone, that the majority of the action is happening within the so-called growing media, or you can call it a soil, although this is an engineered growing media. And so we were quite shocked, I must say. Immediately, one of the very low-hanging fruits that we wanted to show was that within a proper proportion of humans, plants, and an environment, that we wanted to dissuade the EPA from continuing to say that plants would not have an appreciable effect on the environment at scale. So really quickly, could we, in a period of time, reduce the CO2 levels by 1,000 parts per million, because that is the amount that has been determined by Satish et al. At Harvard and Syracuse to be the amount that would affect executive functioning and potentially long-term health outcomes over time. So that would just be the low-hanging fruit. Can we provide a better environment? Can we reduce the CO2 levels? We were reducing the CO2 levels within an hour at 1,000 parts per million. So that was a very quick thing. But one thing that the thing that we were very surprised to see is that we actually saw within 20-something subjects within an hour, a statistically significant impact on both heart rate variability and breathing rate from the plants. That was really, really surprising to us because no one, least of all the cardiologist, actually the cardiologist that we were working with from NYU was the one who was running that whole aspect of the human factors. So that I apologize that I don't have the group. I should have a group slide of everybody that's involved here, but there were people taking cognitive tests, cognitive scientists, we had physiologists, we had aerosols, chemists, and many different people sort of interfacing and sort of setting the protocol for this test. And we weren't expecting that result. And then it became a question of how are we getting that result? What is happening? Is it really the CO2 that's changing that? And we actually decided that even though, based on the literature and what we could know, that we couldn't be sure that it was the CO2 that was really making that very quick change. So it had to be something within the air, but we don't know what it is. Is it the microbial? Is it the so-called aerobiome? Is there, in many, obviously there's a lot of hypotheses that are emerging as well about the concept of living water or of living air. So we still obviously don't know. These are big questions that we have. And so, we interface with biologists and plant physiologists and others that are in soil microbiologists, et cetera, to really start to understand, what are these relationships? What are the interrelationships? How can we start to correlate findings? Very early days and in a way quite slow, because it's very hard to get all these folks together, to be looking at something simultaneously. And what would be the point of doing it? And once again, we come back to our starting point. Because we are architects, we're working backwards from the ecosystem. We're saying we have to deliver this ecosystem. If we don't know why, for example, we're able to affect heart rate variability or breathing rates, then we're going to have to chase it down. We're going to have to figure it out, because at the end of the day, we are responsible for that design, and we're responsible for that system, and we have to sign off on it. So going back to PSAC 2, to scaling up, there's obviously a lot of questions socially about reintroducing living systems within a built environment. They're dynamic. Our buildings have not just, one of the main reasons why we've designed buildings and cities to sort of keep out living systems is they're unpredictable. They're dynamic. They have a maintenance requirement. And the issue of predictability, or sort of the sort of pretend stasis, right? When we study statics, right? And strength of materials, and we pretend that things are going to be quite durable and very predictable. That is obviously not the behavior of living systems. So to have to sort of design with and flow with the behaviors of living systems is a whole challenge, both technically, obviously, and socially. Beyond that, the inhabitants, or the folks working at the Public Safety Answering Center, I love the anecdote that they are constantly going, whenever we're maintaining, this is we maintain it, it's on cruise control, as we say, quote unquote. Now it's been there for 4 years and running, and we only maintain it. We cut down, and we sort of check root rhizosphere, Reynolds numbers, and sort of density of growing media and all of that about once a month. And every time the droppings fall on the floor, folks from inside the building are sweeping them up. We don't have to actually sweep them up. They take them and take them to their desks, and they put them in water. So this wall is spreading out throughout the entire building even before we have replicated it. And everyone's asking, when are the tomatoes and their other vegetables coming? When are we going to convert this to food growing? So that's an amazing anecdote for me, because we can't wait. At Yale, a lot of our research is actually looking at, we're studying mostly the food growing or the edible plants mostly. At PSAC 2, you just saw golden pothos, which is a very robust and resilient plant that can handle a lot of insults and maintenance and other things. But this is just sort of to sum up. You can see, right, that sort of all of the different scales at which it's typical that people might work at multiple scales, but it's going to be very reduced. It's not going to be that they're working all the way across, let's say, the scales and the disciplines that are sort of captured within this summary. If we were to sort of zoom down as to really where we are, right now with a lot of this, as I said, we're interested in a sense, ramifying, in a sense, all just like I mentioned with the solar energy, we are ultimately always looking to amplify the characteristics that are, in a sense, remediative or productive. So to look at literally all of the things that we kind of have to do for indoor air quality, if we were going to start over on this right-hand side, very, very basic things, as I said, could be CO2 balance, could be energy outcomes. I didn't even talk about that, but of course, obviously, one of the main drivers of integrating vegetation into roofs, into walls, and into the interiors is a reduction in energy consumption and a much more pleasant environment relative to what we call psychometric profile, or the relationship between humidity and absolute humidity and relative humidity. We can feel already in this room, even though it's quite nice outside, is a little dry in here for probably what we would want. And so our mechanical systems are very, very good at taking out humidity in the summer, very poor at adding humidity without becoming pathogenic. And once again, that has to do with the low diversity that you have inside and inside systems, among other factors. So ultimately, just to sort of sum up, we would never think about, as architects, designing literally growth media, or, or we might think about the effects. But in terms of the choice of plants or plant characteristics to integrate into an environment, the degree of functions and other things that the scientists are looking at are sort of, epically sort of beyond what we would have considered in the past. We were really just focused on the impacts. But now what we're interested in is not only this feedback loop going from the deployment environment, the room that we have to deliver, or the building, but dramatically enlarging the number of people that are involved in how we decide what we do for organizing cities and buildings. And literally, how do we look at them? How do we analyze them? How do we value what they are doing and how they are doing? If we think about the built environment as something that also has to accommodate, let's say, the functioning and the well-being of plants, these plants are not going to do much for us if they're not photosynthesizing well, right? Or if they're not happy, literally. So we think about, what does the plant want? What does the plant need? And to start to design literally for both human characteristics. Before, indoor air quality might have been thought of just as a kind of human or anthropocentric based requirement. But now, in thinking about buildings as ecosystems, we have to think about the relational quality of all of the living systems that might be outside, in and around the building, inside the building. And this is just a very, very, it looks like a very reductive start, and it is. For as much as we are including many more criteria than we used to into the sort of analysis and design of building systems, it's super, super early days. And I would say that almost where we are right now in the 21st century is we've spent millennia, as I said, keeping the living systems, other living systems out of our environments, trying to pretend that we're controlling or predicting all of their behaviors. And there's really a huge paradigm shift now in trying to think about working with, if you will, extended ecosystems and environments in the design of future building environments and urban environments. Thank you. So I don't know if there's any questions. Oh, thank you so much.
Yeah, we can start with some questions. Charlie, go ahead.
Space station, people living in space, and they produced a book called Bioastronautics, which you can get online. So that's one source of information, but it was so dated when I looked at it. I'm wondering, how would you update that?
Yeah, that's a great question. In fact, actually, when we first got started, I cannot believe how long ago it is now, but it's a couple of decades, we began working with Bill Wolverton, who was a NASA biologist. He was one of the biologists that was leading the NASA Biohome study, which was basically looking at that ability for example, the rhizosphere to remediate VOCs, et cetera. And we're in good touch. In fact, we just had a really nice panel with Dr. Ray Wheeler from NASA, who is one of the plant physiologists there. I think that we're so indebted to that work, even if it may seem dated, and it has been difficult for us to reproduce some of the findings. So we've had to kind of go all the way back from scratch on some of that stuff. I think we're really indebted. I think there's a lot of information there, but I definitely think that how would we go about updating that? Our criteria is slightly different, obviously, from NASA because we're looking obviously at terrestrial environments. So their necessity to kind of really look at that closed loop, right, between, you know, like literally humans and that kind of interior environment without any inputs it puts a different type of pressure on the work. I think that I think the biggest problem I will say is, and this is, and I'm glad that you brought that up because it brings up the social difficulty of multidisciplinary relationships. A lot of the NASA work was really kind of discounted because of the context within which it was produced, and maybe, you know, there was a little bit of short circuiting going on, you know, and so I think that we're kind of caught in the middle as architects because we're very interested in that work, but we understand that, you know, it didn't follow maybe along the sort of classical siloed trajectories that one might expect in, let's say, in those related fields. And so that's where work gets lost, because I think NASA was, maybe the context was much more applications oriented. And I think that it sort of fell by the wayside, maybe because of claims that were not followed through, or maybe, you know, didn't add up entirely in terms of especially like terrestrial environments. So we never really anticipated having to get into the literally sponsor the fundamentals of this. So what ended up happening was, as architects through PSAC 2 and other projects, we ended up sponsoring fundamental research of our colleagues, right? Because we don't really necessarily need to get down a million rabbit holes, and we don't have the wherewithal to do it. But increasingly, I think what our next step is to really prove that big projects like PSAC 2, just to give it an example, it was when we first started as a 1.2 billion with a B a budget. We were able to siphon off just a few million for that installation, and then it ended up being much more in order to create the zone that would be sort of like hived off. So you really have a controlled setting within which to work. I think that that we need to leverage buildings much more in order to fund fundamental research in those sciences. And I think that, and the way we were able to talk to the Bloomberg administration about that, which was really, really incredible that they were sort of receptive to that. We just said, look, is it more or less risky to go with your HVAC system that can really only keep people alive for 7 to 10 days, especially in a big server building like that? You weren't going to really be delivering adequate air quality within less than 2 weeks if the exterior air intake had to be shut off because of a compromised situation on the outside. So if that is the programmatic criteria, then there must be some funding for research to really look at novel concepts. So why do I say that? Because I think, you know, you mentioned NSF and you mentioned DOE and others, they're not going to pay many millions of dollars for us to scale up these test beds. It's just not going to happen. NASA had an incredible opportunity back in the day when they were putting a lot of resources towards this. And maybe it is a shame that it didn't go further, but we have to go further. We don't have really the choice, because within the context of climate change and rising CO2 levels and sort of this catastrophic interrelationship between declining immunity and biodiversity, we must figure out how to make our urban and built environments more biodiverse. We're not going to figure it all out at the lab scale. So, but what our point is to try and create a new model that sends fundings from large scale public works buildings into the labs, right? That's the difference. And it was always going before outwards, right? Always from fundamental towards buildings. Now we're saying, let's reverse that and try and reverse the funding stream from buildings and cities into fundamental.
Yeah, I couldn't agree more. I'm just going to remind people online to post questions. They're being relayed to me. I think Charlie has a question.
It's fascinating stuff. And if I can indulge 2 questions, one being an interest question, and then one more technical thing. So my general interest question is air turnover rates or protecting the building, for example, from attacks, let's say in that particular instance. Have you had the chance to look at pathogens in thinking about COVID and viral transmission?
Yeah, that's a great question. Actually, my my former PhD student at Ahu Aidoyan, who is now a tenured faculty at City College. She is working with chemical and biological engineering, and they're being supported by the Army Corps of Engineers. Prior to COVID, looking at sarin gas and other things in the growing medias that they're testing, which are relatives of ours. Of course, we are constantly rethinking what the growing media is going to be. That's part of the research. But to neutralize those types of agents, there has been research, and I believe they're about to publish those findings. We are now working with chemical and environmental engineering, Crystal Pollitt Lab and others at Yale. We will be testing with some of the viruses that, well, you mentioned maybe one in particular, but to set that up is tricky for us, but we definitely have a keen interest in that. I think it's a great question, and we definitely need to do that.
Yeah, I can understand where that's a human subject issue. So my other question is about the relative mass of plant biome to airflow rates, and
Yeah.
we think about building turnover
Yeah.
rates for the air, and
Yeah.
then I'm thinking about rate limiting diffusion and with the plants and how fast
Yeah,
they're turning
yeah,
over air.
yeah.
So sort of are there opportunities to build like whole walls where the air is moving through the plants, or what's the
Yeah, that's in fact exactly what this one is. It's everything's moving through. I showed briefly an image of the back of that. So this is completely connected to the HVAC system, and there's a plenum behind this. Unfortunately, I can't show everything with PSAC 2 because it's a classified building, so we're not allowed to show the plans and sections. Otherwise, I would absolutely show that. But there is a plenum wall behind. There's a plenum behind it, and what we are doing is exactly as you point out, testing the flow rates and the relative residence time that we need with different types of processes. So for example, maybe one of the holy grail that NASA was very involved with, which is the reformation of VOCs molecules by the root rhizosphere, that really requires a certain residency time that is not going to be with the kind of flow through rates that you have in typical HVAC or the volume. So this is a classic case of where we're thinking about, like in PSAC 2 pulsing, or being able to have a different type of pulsing flow that is associated with plenums that is different from what you have in a typical HVAC condition. There's also, and then trying to think about that relative to parallel tracking with the programs, like the diurnal programs that you have. This is a 24-hour building here for obvious reasons, because it's a safety answering call center. So that's going to be tricky, but that's one of the biggest issues. The lowest hanging fruit, of course, is CO2. That's why we were showing the data on that. Reducing CO2 is something that we really do feel is kind of basic. The much more difficult things are reforming and taking and remediating, can we, for example, inoculate the microbiome with so-called probiotic inoculation? That's also a very, very difficult issue relative to your question is what is viable and when is it viable and how, in terms of the way that we're shaping airflow from, let's say, inlets into rooms and exposures. This is another area that I didn't get into that has been a long-standing research for us is flow control, and really transferring some of the emerging advances in flow control from aeronautics into buildings. We do feel that, like, if we're talking about providing a so-called healthy stream or a kind of, biodiverse aerobiome, and of course these are hypotheses, then we would have to do much better in terms of the way that we're targeting air quality exposures in buildings. And that would obviously affect everything from exposure to pathogens and other things.
Again, if there's a last question, we're right up against time, but I'd like to give anybody the opportunity to ask. If not, I have just in parting words, as you're also jointly appointed with the School of Forestry, as I am architecture and engineering, I really would love if you would just give us your insights on the best way to foster these kind of communications across disciplines, or what is the way that you get your foot in the door sometime? Because I feel like a lot of us may have opportunities to work in buildings rather than with the DOE, where there's big budgets. And thinking about those opportunities, I think was an important point that you made.
I was really lucky that early in my career, I was introduced to a kind of framework in Paris during the Mitterrand administration that had a budget for every single public works project that would be research. And I think just with the money, they will come. Do you know what I mean? So, and I think that that's what we tried to recreate a little bit at CASE, the center that Forrest mentioned with SOM. I think that I think if it's well defined in terms of what someone's role is going to be and what they could get out of it, then interdisciplinary work will flourish. The problem is that is really being able to define. Someone's got to be the expert integrator, right? Someone's got to really define what if one is not used to these kind of very, very large lateral frameworks, then they will need to know exactly what their role is, because they're being rewarded to climb a silo, and it's just that's the way things go. And I always say to the students, we need to be clearer. We need to be hyper clear about what our discipline is in order to collaborate with other disciplines. I'm still struggling with that myself after decades. So it's way too long to say I'm not sure I'm a good person to give advice on that, but I will say that we keep trying and that we have wonderful collaborators, and we're very, very happy with that. But the institutions and the reward systems are obviously greatly mitigating against or working against allowing people to find their way into a kind of lateral framework. And that's a real shame. It seems that, just there isn't the expectation that they, that a lot of times it will be rewarding, I think. And I absolutely don't think that that's any one sort of, like, I think individuals would love to do it, but they just feel that it's too much of a risk. And, we have to, it's up to administrators, senior faculty, such as us, it's up to all of us to create a much, much better institutional sort of reward system that will protect people to travel slightly, you know what I mean? And to be able to allow more criteria, let's say, into their research. We have to be proactive about it. And, in a very dumb way, I mean, one of the things that we say, to our administration, you need glue figures. You need people, postdocs or others that are interested in working across. So maybe it emerges from the interest, but they have to be rewarded. So.
And look online. I think the next speaker is being posted. There's more great events to come at the Andlinger Center. And thanks everybody for coming.